All right. So yeah, welcome everyone to today's webinar titled The Importance of Thermal Conductivity in Bio-Based Building Materials. My name is Arya Hakimian. I'm an application scientist here at C-Therm Technologies. Just a couple housekeeping items. Take note of the chat box on the right of your screen. My colleague John Clifford moderating the session here today. He'll be posting different little bits of information throughout the session, links to different application notes and resources that come up throughout the session here today. Also, if you do have any questions, please feel free to put those into the chat box. We will be going over a little bit of a Q&A session near the end as those come up. But that being said, we'll get started here. So a little bit of background to before we get into the main component of the session here today. Just for those that may be new to C-Therm, not as familiar with us. Really what we do is our purpose statement is simplifying thermal conductivity testing for the materials of tomorrow. We do this through primarily the transient class of thermal conductivity measurement techniques, and this will be discussed throughout the session today. Our flagship product line is called Trident. Trident is a modular system. It was developed with the idea it's better to have options. There are 3 different methods that are available on the platform. The MTPS, Modified Transient Plane Source, which is the sensor on the far right. That's C-Therm's proprietary sensor design. This is the one that will be, I will say, most heavily featured in today's session. But the other 2, I will make note of. The one in the middle there, the needle probe style sensor, that is the transient line source, TLS. The TLS has some good applications for testing a range of geological samples, soils, soft rocks, aggregates, also applicable to testing things like polymer melts, more chemically aggressive fluids, and things of that nature. And the last one, the one on the far left, the yellow sensor, that is the more traditional transient plane source, or TPS. This one will be featured a little bit in our session here today as well, but just a little bit of an overview for everyone if you weren't familiar. And with respect to the different methods, there are a range of different options out there, ones that we offer, as well as, other options in industry. If you're new to thermal conductivity and just kind of looking to get some understanding of these different methods, maybe learn a little bit more, we do have a free method selection guide available on our website. And again, colleague John has posted these links into the chat as well. So definitely feel free to take advantage of those if you do want to do a little bit of research on the different methods and kind of what they're applicable for, what types of samples, and where their strengths and weaknesses lie. Last thing I'll just highlight here is a little bit of a client testimonial. We're very proud of the clients that we support, and it's always nice to get some feedback here. We, again, have a range of different client testimonials available on our website. Pulled this one as it relates to kind of some of the work that might be highlighted here today. But the group noting that they're using the MTPS method to do fast thermal measurements, much faster than their old equipment. They're also highlighting the ability to determine thermal effusivity, which was relevant to their building materials that they were testing, and highlighting the support from the C-Therm team and ComF was great. And just noting that ComF is one of our distributor partners in Poland. So just noting we do have a range of different distributor networks around the globe. So, if you're kind of phoning in here today from North America, Europe, Asia, we do have a range of different support systems in place to help you out. But that being said, that kind of covers a little bit of background information on C-Therm, who we are. Now we'll kind of dive into the main bulk of our session here today, which is surrounding thermal conductivity of bio-based building materials. So when we're talking about building materials, oftentimes this is looking at, whether it's residential or industrial buildings, um, really looking at heat transfer and where heat loss occurs. So a lot of the effort putting into these different materials is surrounding that aspect. Looking here at the image on the left, looking at the building envelope, these are typically used to describe where the heat loss occurs, and depending on what resources you look at, these numbers can change a little bit there, but generally speaking, the walls and the roofing will make up a very large portion of where that heat loss can happen. As you can imagine, those are what makes up some of the largest surface areas of these different buildings. But of course, there is loss through the windows, doors, also going into the ground level through the flooring as well. Um, but where this comes into play is, of course, you want to minimize that heat loss. You want to reduce these, hotspot buildups where more heat is being lost than others. So the image on the right there, it's a thermal imaging of a building where you can see that different locations do have different overall temperatures that were recorded. And this is, of course, related to the insulation capabilities at the different locations. So whether there's different materials being used there, different structures in place, and things of this nature. Now, when we do talk about building material types, I mean, it's quite wide ranging. Again, whether you're looking at something constructed with a metal or a wooden frame, what the walls are made out of is, the exterior, is it a vinyl exterior, brick, natural stone, cement? There's a lot of things at play there. Also looking at things like what's going on inside of the wall, so the insulation, how's that being applied, things of this sort. So quite wide ranging, I would say, in the types of materials that can come into play. But primarily for our session here today, we will be focusing on mostly insulation type samples or materials where insulative properties are of interest. And of course, what insulation does, they're used to help reduce that heat loss. So they reduce heat transfer, helping to maintain your internal temperature conditions. So whether that's in the wintertime where you're trying to retain that heat energy inside, or conversely getting into those summer months where you want to keep it cool, insulation helps maintain those desired settings. Now, traditionally, you see common materials, a lot of synthetic material types. These include things like fiberglass, polyurethane foams, polystyrene, whether they're extruded or expanded polystyrene. These are, kind of more traditional options that have been in place. However, again, what we're focusing on here today is more of a look at these bio-based alternatives. So a bio-based material, at a very high level are those that are made from renewable biomass sources. These can include things like plants and forestry materials. Um, comparable performance has been noted. These types of materials have been investigated for a few years now, and there are studies showing very comparable performance, with notably lower negative environmental impacts. Some other aspects to the materials, such as things like the moisture management capabilities, mechanical strength. Of course, there's a range of criterias that need to be investigated. But for our session, of course, we'll be focusing really in on the thermal characteristics of these materials. So some common bio-based material types that might see out there, and some that we'll discuss today, include things like cellulose, natural fibers like hemp, wood, flax, etc. So coming back to our main topic here, which is thermal conductivity. Again, for those that may be new to the topic, I'll just kind of do a very quick high-level summary here. But effectively, thermal conductivity describes a material's ability to conduct heat. At its core, it's an intrinsic material property independent of the size or the shape of the sample. So again, whether you have kind of a small chunk of, material A, or you have a massive sheet of it, the thermal conductivity of that sample is effectively the same. Now, of course, as we kind of go through the session, you'll know certain methods will require different sample sizes to accommodate the measurement requirements, but inherently, whether you're testing a small piece or a big piece, the results will be the same there. Now, related to thermal conductivity, but with a slightly different approach, is thermal resistance, or sometimes called R value. Especially when we talk about insulation, this is something in the industry that will be of interest to some folks. Thermal resistance is an object property, which means, unlike conductivity, it is dependent on the thickness or the size of the sample that you're working with. So it's just really good to make that distinction. In this case, for thermal resistance, a higher value means it has a better insulative performance. So R value, quite simply, it can be calculated by dividing the thickness of the sample that you're working with by the thermal conductivity of that material. So all the methods that we will be kind of covering here today provide you with a value for thermal conductivity. That's part of the core measurement. So if you needed to get an R value of the sample, you would simply take the thickness that you're working with and divide by those results. I also do want to make a distinction here between the different, I'll say, versions of R value. There's kind of R value, which has the feet squared, Fahrenheit, hours per BTU. This is the imperial units that will sometimes be used depending, again, on where you are in the world, whether in North America or elsewhere. But the RSI value, again, it can sometimes be used interchangeably here. This is the one that has the standard units. And it's just good to understand because they are quite different in the absolute value there. So if you ever see something in RSI and you need to convert to R value or vice versa, there's a simple conversion factor that you can use to do that. And just a last note on R value or thermal resistance here. A lot of the times when you're looking to tailor or fine tune a specific R value for a system that you're working with, really you have two options. You have scenario A here, where you can simply increase the thickness of the sample that you're working with. So looking at sample 1 and sample 2, the K value or thermal conductivity shown here as X is the same in both cases. So it's the exact same material. It's just, the sample 2 is noted here to be twice as thick. And in this case, of course, what you'll have is the R2 will be greater than R1 for that scenario. The other side is kind of seeing on the right there, scenario B, where you're actually decreasing the thermal conductivity of that material. So you're using a different type of sample. It has a lower thermal conductivity, but maintaining the exact same thickness. And again, in this scenario here, the thermal resistance of R2 will be greater than that of R1. And I guess depending on the applications here, or really the system that you have available, kind of the size and the space that you have, one or the other of these could be employed there. Typically, scenario B, you get the benefit of space savings, but this typically comes at the cost of more expensive materials. So again, there's always that trade-off that needs to be looked at. So coming down to the test methods that we'll take a look at here today. So again, we focus primarily on transient-based techniques. Again, these are things like the transient plane source, modified transient plane source, TLS, and of the sort. But there is another general class of methods which are steady state in nature. You can include things like the heat flow meters, guarded hot plates, things like this. So they are two very different approaches to the measurement of thermal conductivity. Again, certain benefits and advantages with kind of each. I'm not going to go into a really full in-depth explanation on this, but I will just highlight some aspects of steady state methods just for those who are looking to kind of get some background knowledge there. Generally speaking, these are a really good option if you are dealing with low K insulation type samples, foams, aerogels. This is really what they lend themselves well to. They operate based on a heat flux measurement. One thing to note, though, is the results that you're going to get from a steady state measurement, just based on how they're set up, is you can kind of view it as almost like an average of across a very large surface of material. One thing you lose, and something I'll highlight that's a benefit with transient, is the ability to detect spot-to-spot variations or very, very small differences throughout the kind of the side-to-side differences within a material. Steady state methods are generally not suitable for high K or anisotropic materials. And one of the limitations is they have some fairly strict sample requirements based on the plate geometries. So in the diagram on the left, what you're seeing is the sample is actually placed in between two plates. One's a hot and the other is a cold side. How the measurement works is there's a differential applied between the two, and the sample in the middle will eventually approach what's called steady state condition, which is of course tied to the name there. But these samples do need to make really good contact with the upper and lower plate. And generally they need to be quite large. Generally speaking, you're working with samples, kind of a standard size, having a material that's, 30 centimeters by 30 centimeters length width isn't unreasonable. The other thing that we'll highlight is your testing conditions are somewhat limited here. So doing representative testing in different humidity, environmental conditions, there's certain limitations there. And inherently they have longer test times, just simply related to how the measurement is performed. Steady state methods will always take longer to perform the measurement than a transient option would. But again, steady state lends itself well to these insulation sample types, depending on like what you're looking to measure, and some of the standards to maybe look out for: ASTM C177, C518. Those are among some of the more popular ones in industry. But again, our focus of the talk here today really is going to be on the transient methods. And for us today, primarily focusing in on the MTPS, the sensor on the right, as well as a little bit of information on the TPS, the yellow sensor on the left. TLS, again, not really featured heavily in today's session. We have a range of different webinars from the past that do focus on the TLS and different application notes that are available if that method was of interest to you. So why transient? I kind of mentioned it when we were talking about steady state, but really, number one, it really allows for representative testing conditions. So whether that's a controlled atmosphere, varying temperature, pressurized environments, these sensors lend themselves quite well to be essentially placed in these different conditions, different setups to accommodate that type of measurement. And really, we like to advocate this because to really get good quality data for your sample, testing it in a way that's truly representative of the application in which it's going to be used under those conditions is going to be the best way to get that good quality data. Mentioned faster than steady state. Again, just inherent to how the measurement works, they will always be faster. Some transient methods will provide results within seconds. Others, a few minutes. Typically for steady state options, measurements that'll take at least an hour or more. Again, that's well within reason to be expected. And then lastly, we offer generally a greater flexibility on sample type and sample size. So we can do different methods, can measure solids, liquids, powders, etc. And generally quite small. So a size for a measurement on the MTPS, for example, you can get away with something that's just, a few millimeters thick, approximately 20 millimeters in diameter. So we'll first start with a little bit of background information on the MTPS, some examples here. So mentioning it's a single-side sensor, provides the measurement of thermal effusivity as well as thermal conductivity. Conforms to ASTM D7984. The software for the MTPS offers automated data processing, so it is amongst one of the simpler methods to get set up and running with. And it's also the fastest. So the MTPS provides measurements within 1 to 3 seconds as a standard measurement time. Kind of noting here, it is also very versatile, very flexible on the samples type that you can work with. We have MTPS pressure cells, so testing under different gas environments, different pressure conditions, across a broad temperature range and under saturated environments. So it is a very versatile sensor type. Here we just have a little bit of a method comparison on some samples that were tested. These are looking at some more traditional rigid insulations. These weren't bio-based, but just a few different samples that were obtained, tested on both a heat flow meter and MTPS. These are, again, quite insulative in nature, but thermal conductivity results across the board were well within 2% between the two different options. The big difference to highlight, though, is that the heat flow meter test times, to get one data point, it was over an hour, whereas the MTPS test time of about 5 minutes, we got 5 measurements. So there's when the measurement goes, there's a little bit of a cool down time associated with it, but you're getting multiple measurements in that given time period compared to a steady state counterpart. One other thing to highlight here is improving insulative performance with fillers. This is something that in different industries, you're looking to tailor the thermal performance. Sometimes you want to increase the thermal conductivity. And, in this application space, a lot of time we're looking to improve the insulative performance or decrease the thermal conductivity. So using these different types of fillers, these can help tailor those systems. Natural fibers and recycled materials can often be employed in the production of kind of these green composite materials. But whenever you're adding a filler to a sample, there are certain things that need to really be controlled for and understand how it's impacting the sample overall. One thing that we've really focused on in the past few years and across different industries, this one is looking at a polymer-based material with a conductive filler, but again, applicable to any sample type, is filler distribution. If not controlled for properly, what you can get is things like hot spot buildup or simply uneven performance across the surface of your material. In this example that we're showing here, this was, again, I mentioned a polymer with a conductive filler. Measuring at different locations, as we can see, resulted in quite a range of thermal conductivity values. But we can correlate that in this example to the filler at that location. So those lower values, those squares in green, were areas that had less filler present compared to the image or the square in the top right, which is very densely populated with that filler kit coming in at a much higher value. So the MTPS, because it's a single-sided method, it really lends itself quite well to do this spot testing, to be able to map out sample performance based on the fillers that may be employed. So I will just kind of pivot now to the TPS, give a little bit of some information on this method as well. A few big differentiators to take note of. First off, it's a double-sided sensor. So inherently from your setup, you're going to have 2 samples to do this type of test. So one sample is going to go on the top and one on the bottom side. Whereas the MTPS measures conductivity and effusivity, the TPS method does conductivity and thermal diffusivity. So a little bit of a difference there. With the TPS, we generally describe this as best for more advanced users, simply related to the method complexity. It's less automated, I will say, than the MTPS. You as a user have a lot more control over the settings. So inherently you can adjust these, so things like the time and the power parameters. Those are in the user's hand as to what they're set to. But because of that, there are a few extra steps that are required. There's a manual verification process you have to run through. There is a data validation and adjustment refinement process that is done. It simply requires a little bit more input from you as the user. But one of the main benefits is that it doesn't require a contact agent. So certain materials, not foams and insulations, I will say, primarily other sample types, but at a certain conductivity range, some methods like the MTPS would require the employment of a contact agent between the sample and the sensor. Again, this isn't required for all materials, but where that does come into play, certain materials that may be hygroscopic in nature or absorb that water, that contact agent that's employed, might make it not a technical fit. So the TPS does provide some really nice complementary aspects here to the overall options on Trident. And one application where this comes into play is testing of concretes or cements. Depending on the conductivity range, again, where you're falling, but Kind of the example that I'll show here, this was a hygroscopic material. So if you put a little bit of water onto the sample, it's going to absorb into the material over time. The flexible design of the sensor also reduces the risk of damage here. So these really rigid solid samples, if you're not careful, you could potentially harm the sensors, but flexible TPS, kind of a really nice fit there. And as I mentioned, it's more complex than MTPS to operate, but still the TPS will be significantly faster compared to a steady state method. TPS also conforms, I should mention, to the ISO 22007-2 standard. And here just showing some thermal conductivity results. Again, kind of average K was approaching about 0.52 watts per meter Kelvin at multiple test locations across the surface of those samples. But really next then, kind of the last part of our session is taking a look at some different publication highlights where we're going to kind of see how these methods are employed across a range of different applications and sample types with really a focus on these bio-based materials. So the first one we're taking a look at here, this is heat and sound insulation applications of pineapple aerogels from pineapple waste. So this is a group, so noting the researchers out of Vietnam and Singapore, so some joint collaboration work here. The idea behind this paper, I'd say the reasoning for it, was looking at partially the agricultural contributions to the greenhouse gas emissions. So kind of pulling some data here, noting that about 25% was associated with agricultural contributions, so forestry and other land use. A significant portion of this is attributed to the burning of agricultural waste. So, of course, if we have a way to repurpose that waste, then it kind of reduces that overall impact. And specifically here, they were looking at pineapple waste. Some few pineapple stats for you guys, but pineapples contribute to over 20% of the world's production of tropical fruits. According to the Food and Agricultural Organization statistics, approximately 27.4 million metric tons were generated globally in 2017. And of that, about 50% of that production ends up as waste. This is because things like the crown, the peel, seeds, core, as these things are processed, a lot of those parts mentioned there are simply discarded and need to be disposed of, and ultimately, a lot of the times end up being burned. So what the research was looking at, if there were a way to take some of that waste product and repurpose it in another way. And what they did was do that, take these pineapple fibers, so if they're processed, turn them into fibers and use them as a precursor material for novel pineapple fiber aerogels. So these aerogels were produced using an adhesive agent, polyvinyl alcohol, and DI water, followed by a freeze drying process. And in this study, they were primarily focusing on the thermal and acoustic insulation properties. That was the main things that were investigated. And you can see an image of the rolled aerogel blanket there on the right, with a kind of a view of an SEM image of the kind of structural components on the top right there. But just kind of diving right into the thermal conductivity results and some of the conclusions that they drew from the study. They noted that with increasing pineapple fiber concentration by weight, it had a link to the porosity that was generated within the structure. So more fiber resulted in lower porosity. And what that ended up affecting, of course, the thermal conductivity, the lower the porosity, the higher the K went. So actually having a lower amount of fiber, having higher porosity, did result in the lowest thermal conductivity, or view that as the best insulating material of the series that were tested. But this was a really novel application, kind of demonstrating how those fibers can effectively be used as an eco-friendly and cost-effective alternative as a building block for insulations. They were noted to have extremely low density, so very lightweight, with good mechanical strength, as well as low thermal conductivity. So, it suggests the potential for other high waste resources to be repurposed in a similar manner. And actually, there are a few other papers out by this group where they look at different materials. I believe there was one on coconut fibers, kind of a range of different recycled produce. All right. So the next one taking a look at paper is the hygrothermal properties of bio-insulation building materials based on bamboo fibers and bioglues. So this is some work coming out again, some joint work, some researchers in France and Vietnam. So part of the paper and what they focused on a little bit is the influence of humidity and saturation in these samples, and how that affects the insulation properties. So high moisture level is a risk for overall building energy performance. So it has to do with the how ventilation in these buildings are set up, and how that affects the overall flow and net performance in these systems. Things like mold growth are, of course, things that want to be avoided, and overall a loss of the insulation or the insulative property of that material. Now, these issues can be addressed by using materials with what's known as high moisture buffering capacity. So this was something that was investigated in this paper. And biomaterials in general, so based on natural fibers such as hemp, flaxseed, straw, in this case, bamboo, which was they're looking at, are of great interest because they're, of course, renewable, low carbon materials, and they are noted to have good hydric and thermal performance. So a little bit of an overview in this paper. They are looking at bamboo fiberboards. They were manufactured using different bioglues. The hygrothermal properties were investigated based on glue type. So they had a few different sample mixture configurations. You kind of see in the table on the right, those the different components that were introduced into the various samples. And as I mentioned, moisture buffering and thermal conductivity performance were the main aspects that were investigated in this paper. Here I just kind of included an image of their setup. So again, when you're looking, one of the things to keep in mind, again, is that representative testing. So, having a really good control over the environment, they kind of have this system, this closed system set up where they can fine tune the humidity, the saturation of those samples, but also, again, the MTPS sensor used here, it can fit, be placed inside these environments in fully saturating or condensing environments. There's no issues with potential sensor damage there. So again, it's a great option for doing these types of measurements. So some of the initial results here, the first one we're looking at is thermal conductivity as a function of the density of the samples that were obtained. So generally you'll see you can kind of correlate trends between certain structural mechanical properties, aspects like the density of the sample as it relates to the thermal conductivity. We can see here that there's generally a net increase in the thermal conductivity with increasing density. One of the things I liked about this is you can see that each sample type, there's multiple test points, kind of having a little bit of an array, a little bit of a spread here. But, when you think about these bio-based materials, inherently there's going to be a little bit more variability in the production of these, at least as these are being developed in more novel applications compared to, more synthetic-based productions, which generally have a little bit more control. You're not dealing with as many potential variables. But again, as we can see, generally that net trend held true. And also they did a comparison of some other composition types, different material types. And we can see things like hemp fibers have some of the lowest overall densities of some of these different studies. And again, correlating some very low thermal conductivity values as they compare to the different samples that are being investigated. But from a moisture perspective or a saturation level, you can see that they did some very interesting work here where they're taking so the graph on the left, basically they subjected these materials inside that system for over a month period, so 30 days, kind of varying the moisture level from shifting between kind of 75% relative humidity down to about 33%, noting on those graphs there. And as we can see, the trend in thermal conductivity of the different samples as a function of that change. Generally speaking, the sample types themselves carried, there's kind of a range where, the highest performer typically and stayed the highest, and the lowest were at the bottom there. But there's also some things to be said. They didn't really touch on this, but the lag observed between when the humidity changed and the affecting result on thermal conductivity. There is some work and some different researchers that I've been in contact with that are looking at things like this, and not only the absolute values, but the net, I'd say, more qualitative changes in the trends that are observed as things like moisture and saturation are being modified. The graph on the right is just a little bit more of a kind of look at the thermal conductivity purely as a function of the moisture content variation. Again, we can see, generally speaking, that thermal conductivity, slight change as moisture increased, but fairly tight results there. All right. The third paper taking a look at is titled "The Development of Wood-Crete Building Materials from Sawdust and Waste Paper." This is a study that's coming out of the UK. So these different X-Crete versus concrete materials, we could do an entire session just on this alone. At a very high level, just wanted to give some background, but traditional concrete is composed of aggregates bonded with a cement paste. This hardens over time. I saw a stat saying it's the second most used substance in the world after water. Water is actually included in the cement mixture, but it's been around for a very long time. I mean, cement is used all over the world. But these bio-based alternatives, such as hempcrete, woodcrete, etc., essentially take the approach of incorporating various natural fillers with things such as in conjunction with lime, sand, or pozzolans, which is just another inorganic material mixed with water. Now, these X-Crete materials, whether it's hempcrete, woodcrete, what have you, they're non-structural. So that means certain applications with concrete, they're used as a structural basis along with their insulative performance. So these different bio-based alternatives are not necessarily going to be able to replace the traditional concrete in all areas of application. But in things like a building here, we can see the image on the right where these, I believe these were hempcrete blocks that were introduced around the structural components. So those wood beams are acting as the support, and these are simply acting as really good insulative capabilities to help tailor that thermal regulation performance. And the other thing with these bio-based alternatives, as I mentioned earlier, they do generally have very good moisture management, moisture buffering capabilities. So there are certain benefits to kind of take a look at there, depending on the application that they're being used for. In this study, though, they were looking at woodcrete blocks produced using sawdust of varying size. So one of the variables that we're investigating is by changing basically the size of the sawdust, how does that influence the net materials that were produced? They investigated the influence of the addition of varying amounts of waste paper as well in conjunction with the sawdust. So again, just using different recycled materials, trying to repurpose those in a way that they can get something novel out of it. Thermal conductivity and mechanical strength properties were the main areas of interest in this paper. So kind of looking at some results here. So there was, again, a range of different materials or samples investigated, those that had different amounts of sawdust, waste paper, tradical lime, and they did actually incorporate some traditional cement into some of these as well as kind of a comparison. The mean thermal conductivity of the Wood-Crete X series was reported in the paper. They didn't have thermal conductivity for all samples, but as we can see, overall, some fairly low thermal conductivity values on the right there, again, indicative of good insulative performance of these samples. All right, and then the last paper that we'll kind of take a look at here today is the thermal transfer behavior of biochar natural inorganic clay composites for building envelope insulation. So this is some work coming out of Republic of Korea. In this study, they were looking at biochar, and just to kind of a little background again on the difference between charring versus burning, because there is a very strong difference there. Burning is, of course, the result of combustion. This is the reaction of a material in the presence of air. And the negative side of this is it results in the release of carbon dioxide gas to the environment. Again, kind of greenhouse gas emissions, things we were trying to avoid or reduce overall. Charring, on the other hand, is the degradation of materials due to heating, typically still at very high temperatures, but in the absence of oxygen. Because there's no oxygen, which prevents combustion from occurring, this occurs through the process called pyrolysis. So what charring does, it produces high carbon containing solid matter, effectively capturing that what would otherwise be released carbon dioxide in the form of a solid char. So again, we have these different types of biochar materials. So different materials can be charred. In this study, they were looking at things like rice husk, coconut shell, and bamboo char. So these were mixed with an inorganic clay composite for the development of building installation applications. So the thermal performance and moisture management were the main aspects of this study. So you kind of see a theme across these different materials, but thermal conductivity, moisture management, and mechanical strength are generally the three primary aspects of investigation. Here, just a really nice schematic they had in the paper, the biochar production process. So you can see they take the biomass, the different materials, and depending on the type of samples, sometimes there's some additional processing requirements, but generally it goes to a washing and drying, and then through pyrolysis, a post-treatment, and then what you get at the end is, of course, your biochar. So the biocomposite preparation, again, a really nice diagram here. So you can see how these were produced, but the biochar powder was mixed with the natural inorganic powder and water. They cured these in a mold, dried the specimens in an oven at a certain temperature, and then kind of left them to dry at room temperature prior to testing. And this is essentially what the samples look like. You can see the ones on the right, the control. So the N was just the, it contained just the inorganic component without any biochar additive, and then all the other ones had different amounts of the three different options that were investigated here in different ratios. Ultimately, from their investigation, from thermal conductivity measurements, they were able to see that compared to the control sample, all the materials that included a biochar component did result in a net decrease to the thermal conductivity, with the greatest decrease at the maximum loading level. Comparing the three different bio sources investigated, the coconut biochar samples exhibited the greatest insulative performance increase of about 67.21% compared to that control. All right, well, that kind of brings me to the end of some of basically the content we wanted to cover here today. Just want to say thank you all for those who joined for our session here live. I just put my email on the screen there. I've had some good conversations one-on-one with some folks after these webinars as it might relate to certain samples you're looking to test, different applications. So definitely feel free to reach out. Also on LinkedIn, feel free to reach out there. I'm always happy to chat. A few housekeeping items on the wrap up here. I'll just highlight. We do have a range of additional resources available on our website. So past webinars, a tech library with different publications, application content. There's a massive amount of these different options available, and for free download. So definitely take a look at those if you are interested in looking further into these applications. Kind of highlighting some upcoming events. So as it may or may not relate to this application space, but a few places where we will be. Maybe have some colleagues that are in this field. Just want to kind of pass it along. But March 21st to 23rd, we'll be at the Silicone Expo in Europe. This is in the Netherlands this year. And then March 19th to 21st, Analytica Vietnam. So again, a couple of places where we'll be either exhibiting or presenting at. So feel free to take note. Some upcoming webinars, again, some different applications will be discussed. We actually have one later today coming up on DMA. So not related to thermal conductivity, but DMA, dynamic mechanical analysis for viscoelastic properties. We have a guest speaker, Jonathan Martins at ARDL, who will be speaking on different on this topic. So if that's of interest, definitely take note. And then later on in the month, I guess it's actually next week, we have a thermal management for EV chargers and power electronics webinar with again, another guest speaker, CoolMag. So they'll be coming, Javier and Moses will be just speaking on these topics. Lastly, again, if you are looking to kind of keep up with us, if you do want to kind of know when the next webinars, all the newest application content is released, this will always generally be posted on LinkedIn. So definitely give us a follow if you want to keep track. And also, if you're looking for next steps, so whether you want to get a quote on an instrument, maybe you want to learn a little bit more, we do have the ability to set up video demonstrations of our system, or just a basic call where you can kind of go over different questions that you have, and we can provide some information on what applications we can support. And yeah, that brings us to the end. So we've got a few minutes left on the hour there. So at this point, again, I'd just like to thank everyone who joined live. I'll stop the recording here, and then we'll go to a Q&A session. So if you are interested in kind of that Q&A, please feel free to stay on the line for that.